it recording? Yes. Okay. All right. Let's start back up. So this is not closed. It does not contain -1. We have concluded. Yeah, like email me if you find -1 somewhere. All right. All right. Okay. So, question 5. Prove that the set is closed if and only if every Cauchy sequence in a set F is closed if and only if every Cauchy sequence in F converges in F, or its limit point is in F, right? So this is biconditional, so we need one direction and the other. Which direction is easier? So a set being closed means it contains its limit points, as we just learned, right? You just learned the hard way that you need to contain your limit points.
So one way to almost trivial by definition.
So this way, right?
If every Cauchy sequence converges in it, then it must be closed because it contains all its limit points.
Yeah, I think that direction's a bit harder though. Because like if you have this, then it contains all its limit points. Boom. Cauchy implies convergence, implies limit point, implies in it, right? So this direction says, suppose F is closed. Let Xn be a Cauchy sequence. Cauchy. Now we know that Cauchy implies convergence. Okay, and so Xn goes to some x, it converges to some x, right? But since F is closed, it contains all its limit points. So X is in F. That's it. Okay? So all you have to use was Cauchy implies convergence, and F is closed means that it contains all its limit points. And yep. Sorry? Yeah, but what we're saying is that we're using that this implies this. The limit point is exactly what a limit point means. So if you were to claim that something is a limit point, you could equivalently claim that there's a sequence that converges to it, right? That's the definition.
The sequence that you can't have has to have a different points.
That's what correlation points. The points which is arbitrary. Synchronous is.
So yeah, so converges means this, but this is equivalent to X is a limit point, right? But then F is closed, so it contains all its limit points. Done. Okay, what about the other direction though? Does someone help me with that?
If every Cauchy sequence in F converges in F, then that means that if we consider the set of all limits of every sequence in F, then that means that it must be contained in must be contained in the F itself.
Yeah, why? So there's a jump in logic there.
Yes.
Yep.
It's like if you don't contain a limit point, look at
Yep. So yeah, you can approach it by contradiction. If you don't contain all your limit points, then there is some limit point, right, which is not an F. Okay, but since it's a limit point, build a sequence that converges to it. But then convergence implies Cauchy, all the way around, and so we just built a Cauchy sequence which does not converge in F. Contradiction, right? So the other direction. So suppose there exists L limit points such that L is not F, then there exists an Xn that converges to L, where Xn is an F, but convergence implies Cauchy, right? If convergence implies Cauchy, then we have showed that there exists a Cauchy sequence which does not converge, does not converge in F, right? So this is a contradiction, and we're done, right? I don't think you guys could see. Did you see the board? All right. Are we all good for this question? What's next? Can I erase this? All right. Have you guys proved that the closure of the union is the union of the closures? Yeah? No? All right, do you guys want to do it? So this is question 6. So you want to show that A, B, A, B. Yeah? Can we do this?
Maybe.
We could do this all together. We could. We could. We'll do it. I'm sure you guys all could as well. So how do we show that two sets are equal? Always, almost always, almost always. We use, exactly, we use one thing, two-way second thing. So we want to show, almost every time you want to show two sets are equal, you're going to approach it this way. You want to show that this, right? And then you want to show that this, okay? Now, to give you guys an idea on how to start, let me introduce some useful notation, which I already introduced. Let this be the set of limit points of A union B, and then let this and this be, as we understand, the set of limit points of A, set of limit points of B. Okay? So now we want to show this and this using that. Right? This is useful notation. So try using it. try coming up with a proof for this. I'll give you guys like 2 minutes because we don't have much time. But I also want you guys to try it. I don't want to just do it in front of you and then you guys say, oh yeah, of course. Like think about it, see where you went wrong. Then, so try doing this part, this part, or doing this part, and then we'll see how things go. 2 minutes.
There's two reasons the sequence will go with topological definition.
What's the difference?
Whether you have to construct a sequence or not construct a sequence. Well, the other
Just open set, same thing, right? Kind of the same. Are you taking topology right now?
I already finished the practice now, but the procedure is
Oh, you took it? I thought this was a prerequisite.
I was able to ask a little bit of history, but it was interesting as well.
I heard he wasn't too bad with the assignments.
We did the algebraic topology, and the further we went into it, the more nonsensical it became. And in the last lecture, he introduced cohomology, and no one understood it. It wasn't an exam, but like,
Sounds
it was fun.
You also waived it prerequisite.
I don't know how the last one.
Yeah, that seems like it. That's cool. He didn't go too hard on you guys, but you learned a lot. So. Or you saw a lot. Maybe you didn't learn it, but you saw it. It was on the board. He wrote something on the board. Maybe you guys didn't understand what it was saying, but it was there.
You went with
Okay. So let's show the first one. Let's show that this is a subset of this. Okay. Well, if we want to show this, let x be in L. So that means x is a limit point of A or B. So that means there exists, or this implies that there exists a sequence such that xn goes to x in L, right? How can we, from this, how can we deduce this? Yeah? Exactly, right? So since xn is a sequence in A or B, there must exist infinitely many occurrences of xn in A or in B. Right? So that means, this implies we can construct a sequence, subsequence, x and k, which is only in A, or x and k is only in B. By the way, throughout this review seminar, I've had a bit of bad habits of not writing the indexing, you know, n and n, and like when I use series, I do this. I don't have any indexes, but in your final, don't do that, because I'm trying to save time. Also, my handwriting's a bit bad already, so, but don't do that. Like, if you have time, just write the indices, you know, because it makes a difference, especially when you're proving stuff about series, right? Okay, so that means this is true or this is true, but what does this mean, right? If it's this, so
It's a subsequence, so it has to converge to a sequence.
yep, so x and k is always going to converge the x, right? But then one of them, this one, implies that x is in LA, or X is in LB, right? So that means, this implies that for everything here, boom, it's here, and so A union B is a subset of A union B. Okay? Yeah? I think this was the much harder direction, because the other way, it's just like, the other way says, let's show that closure of A union the closure of B is a subset of the closure of A and B, right? So how do we approach this? Yep.
We take a limit point either in A or limit point in B.
Exactly.
Yeah.
So without loss of area, let it be A. Let X belongs to LA, then there exists Xn goes to Xn contained in A, same exact thing. There exists an Xn contained in A, such that Xn converges to X, such that Xn converges to X, but if Xn is a sequence contained in A, then Xn is a sequence contained in A or B, right? And so Xn is also a sequence contained in this, right? X is also in this. But Xn is contained in A or B, which implies that X is in L, right? Which implies that A, B, subset of A, or B, or any questions about this or this? Yeah, no? Okay, a bit of a related question. Maybe we can do this a bit fast, but what was it, question 6 or question 2? Does this hold for countably infinitely many sets? So, is it true that
No.
A or union of AN and in N closure is equals to union of AN closure? And let's think about it for like 25 seconds, because you don't know much time.
Intuitively, it's not, because we know that the closure of a set is a closed set, and the union of those, a countable union of closed sets. Oh, wait.
Yeah. So maybe we still need another like
The
this.
countable union of closed sets is not going to be closed necessarily.
So do we have an example?
Example,
You don't think it's true?
it's not true.
Okay. So do we all understand the question? Yeah. Is this true? No. Is what Edward says? The right name, Edward? No. Why? Because take AN, so we just 1 over N, and right? So when you take the closure of the unions, what do you get? So you get 0, union, no stuff, right? So 1 over whatever, 1 over the, keep indexing, right? So 1 over N. Well, I should have just written this, right? AN is equals to 1 N. And then when you take the union of the closures, well, the closure of one point is just itself,
They're just going to be without zero.
right? So it's just going to be this. Yeah. And so no, they're not equal. I thought this was a cool follow-up Does anyone understand, not understand what we're doing here?
It's not,
All good?
that's what I want.
You guys time to write it. I'll erase that side. Are we all done writing this stuff here? Yeah? Now we're moving on from topology. We're going to limits. So question 7. Does the following function have of x minus 2 over x minus 2. If you know whether or not it does have a limit, you need to explain, okay? And why. Yeah. So think about it. From first year calculus, what do we know about limits existing and how they react to existing from two different sides, right? So we used to show that a piecewise function has an existing limit, even now for you guys who just finished B41. I assume that's why we have like 20 more, like 15 more people coming. You have a function that's defined with this, and then x is greater than 0, x is less than or equals to 0, show that the limit exists at 0, you would take it here and then here and show that these two are equal, right? Okay, could we kind of do the same thing here? But instead of saying as x approaches 2 from the left, as x approaches 2 from the right, could we like formalize it maybe by a sequence? Could I have a sequence? Could we consider maybe an equals 2 plus 1 over n, an whatever prime equals 2 minus 1 over n. This is the same thing as approaching from the right, approaching from the left. They both converge to 2,
Yeah, but that limit does not converge.
right? But then, what happens when you plug it in here? Right, so if we plug the first one in here, we get what? 2 plus 1 over n minus 2 over 2 plus 1 over n minus 2. This is equals to 1 over n over 1 over n. This is just 1. Yeah? And now when we write it with an prime, we get, so in terms of an prime, we have the limit is 2 minus 1 over n minus 2 over 2 minus 1 over n minus 2. These guys cancel again, these guys cancel again. This becomes positive because it's absolute value. And so we get 1 over n, no absolute value, over minus 1 over n, which is negative 1. Yeah? So then no, doesn't have an existing limit at 2, because when we approach from the right, we approach from the left, we get different answers, right? And so, side note, this is the same reason why we cannot differentiate the absolute value at 0. Right? Same exact reason. Okay. This. theorem in class?
Maybe.
Sorry?
The squeeze them.
Okay, do you guys want to prove the squeeze theorem?
Or limits or sequences or?
Of functions. You guys proved it for sequences, right?
Sure.
We can prove it for functions. Or, okay, no, I'll skip over it. If we have time, I'll just leave that for personal questions because I'm sure a lot of you guys have a lot of questions, okay? So I'll skip that. Try proving it in your own time, the squeeze theorem. Question 8. So, okay. Does there exist two functions f, g such that f and g are not continuous at 0, but f plus g and f times g are continuous. That's it. So try finding these functions if they exist. If not, let me know why. Well, if they don't exist, then they have to contradict some kind of continuity condition. Alright? But does my suggestion here contradict continuity in any way? I don't know. Well, I do know. You guys don't know yet, so we'll see. Modify two Dirichlet functions. Dirichlet functions like one with rationals and irrationals, and like -1 and like something else, or like 1 and something else, 1 and 0. Alternate. Cool. Then if you multiply them, it's alternating. It won't alternate anymore, right? And if you add them, then what happens? All 0, so it doesn't. So yeah, that does work. I was thinking of a much easier one. Just take f equals to -1 if x is greater than 0, and then 1 if x is less than 0, something like that, and then make g is equals to -f, right? It's like standard example of like -1s, and so you guys can check. But obviously this is not continuous at 0. Because the left limit and the right limit are not equal, okay? But when you take g to be -f, when you add them, it is continuous, right? So you guys could verify that. I don't think I need to check it. Okay. Okay, what about, does there exist something such that f is continuous at, sorry, it's not continuous at 0, but f plus 1 over f is continuous at 0? At 0? Does there exist?
Obviously, that's defined at 0.
continuous at 0. Yeah, it could be defined at 0, yeah. It has to be defined at 0 if you want to make the other one continuous at 0. But maybe it doesn't exist. Yep.
Can have f equals to 2 when x greater than 0, and when x less than 0, we get 1 half.
So could you repeat that?
When x greater than equal to 0, we have 2.
2, x greater than equal to 0, and then
1 half.
yeah. It's your function.
Yeah.
Yeah, I think this works well. Yeah, essentially you think about reciprocals, right? Because when, and it could work for 3, it could work for 4, it could work for 5, because you're taking f and it's reciprocal, but then you're taking the reciprocal of the reciprocals, you're getting f back, and you keep alternating when you're less than or greater than 2. So let's check. When you're at 0, right, so what happens is you get f of 0 from the left, so from less than 0, is equals to 1 over 2 plus 1 over 1 over 2, which equals to 2.5, and then f of 0 from the right is equals to 2 plus 1 over 2, which is equals to 2.5. Thank you. Yeah, so just think about, you can replace this with any n actually that you want, maybe not other than 1, because then it would be continuous, and other than 0, because then it would not be defined, unless you count, some computer science would count n as 0 part of n, right? Okay, last one for these types of questions. I think so. If G is continuous and G of R is equal to 0 for all R in the rationals, then G of X is equal to 0 for all X in R. So let's wait a bit till everybody reads and writes the question. Then we'll answer it. So I have a function, it's continuous. Its value is 0 at all the rationals. Must it be 0 for all real numbers?
That is a similar question in our topology final.
Yeah.
But for all two dense sets in a space.
Q is like a representative of dense sets, right? I think I need to do this, so while you're thinking. Oh, okay, I'm sorry. Just pass it on and we'll have it put on the game. Alright. So what do we think for this one? True or false first?
True.
True? True? Yeah, this is true. Why? So suppose that there exists an x such that g of x is not equal to 0, right? then g of x minus g of r, if you take any neighborhood, you have rationals, right? G of x minus g of r is equals to g of x minus 0 equals to g of x, right? And so there will not exist any r, no matter how close you get. There's no neighborhood, right? Because any neighborhood you think of x contains infinitely many rational terms, right? So any neighborhood of x has infinitely many rationals, but this is true, but then this is not less than any epsilon, right? So no matter how close you get to g of x, you're never going to be less than epsilon when you take a difference in any neighborhood, and so then it's not continuous. G of x not continuous, right? And so by contradiction, you're done. So yeah, this is true. Okay, last question, and then I'll be open for questions. You guys need to raise that one. Okay. So, question 9. Function. Okay. This one's a bit. This one might be a bit hard. I don't know if I could explain it within 10 minutes. So f 0, 1 to r is continuous, and f of 0 is equals to f of 1. Okay, so show. Thank you. Show there exists x, y in the unit interval such that the difference of x and y is equals to 1/2 exactly, and f of x is equals to f of y. So something should pop up. Something that you guys took at the end of the course should spark in your head, like, hey, this big theorem, we should use it. I don't know how we should use it, but it should come somewhere. So we have a continuous function. We have that its endpoints on its domain are equal. Okay? I don't care where it is, it's equal, right? We can have a function like this. Right? Now we want to show, well, this is not 0, 1, but we want to show that there is, a set of 2 points. So you have x and y, such that their difference is exactly 1/2, but they are equal. This is what we want to show. So we have 2 things that we need to show, not just one. Well, obviously the first one's always given. You can always find 2 points at a distance 1/2 away, but it's not always true that they're equal. So first of all, what theorem comes up in your head when you see such a question? What do you think? IVT, right? So we're thinking of IVT. Want to have some kind of intermediate value here, but not necessarily for this function. We want to define a new function.
Distance of the injured.
Yeah, so typical analysis question, maybe not now, maybe C37, whoever takes it. You have some type of question, you have some nice theorem that could apply, but you need to define a new function to apply that theorem. Okay? So to show this, let's define g of x equals to f of x plus f of x plus 1/2. Exactly. minus, yeah, you're right. This is minus. Yeah, so we bring it, yeah, because we want to show they're equal, so we want something here to be 0. Bring it on the other side, yeah, you're right. Okay, so we define this function, and now we need to start building our way to use IVT. What are the hypotheses of IVT? What do we need? We need continuity for sure. Right? Okay. Where is this continuous? Definitely. Right? So g of x is continuous. 2. That's for sure. Let's play around with this function a bit. What do we know about g of 0? Well, that's f of 0 plus, sorry, minus f of 1 over 2, right? But then what do we know about f of 0? F of 0 is equals to f of 1, right? This is equals to f of 1. So then we can rewrite this if we take out the negative, and we have this is equals to negative g of 1 over 2, right? Yeah, because then this is equals to f of 1, right? And so then this will be your base point, g of this, and then so you take the negative and that. So we have g of 0 is equals to g of 1 half. Negative g. What do we do now? Consider cases of g of 1. What do you mean?
Consider how the value of g of 1 compares closer to the positive.
I like the idea, but I feel like it's too brute forcing. Where could we use IVT? Essentially, is what I'm asking. Where could we use IVT here? Because we know that they're equal. What do we know about? What does this say?
Roots where there exists g that is less than
There must exist some root, right? Because you have a function, whether it's positive here at g of 0, you're saying it's equals to some negative of it, right? And so by IVT, we know there exists some root, which implies that there exists x in 0 to 1 half, such that g of x is equals to 0. This is true if and only if the definition of g of x, right? What's the definition of g of x? F of x minus f of x plus 1 over 2 is equals to 0. If and only if f of x is equals to f of x plus 1 over 2. Take x to be x, take y to be x plus 1 over 2. They're equal, their distance is clearly 1/2. We're done. Okay. Thank you everybody for coming. It was nice seeing you guys